Hello and welcome to our lesson on rational functions and asymptotes. So a rational function is basically a function that has a fraction of polynomials in it. So technically we say it's of the form f of x equals p of x over q of x, where each of these, so p of x and q of x, represent polynomials. So again, it's just a fraction of polynomials. And anytime we're looking at a fraction, we have to be wary of the denominator. The denominator cannot equal 0. That 0 in the denominator is not defined. So in this case, we would say q of x cannot be equal to 0. Now we've looked at the parent function, the parent rational function, just 1 over x, or the basic reciprocal function, and we're going to start there again, just so we can refresh, and then we'll look at some transformations, some other reciprocal functions, and talk about, in general, how we can find vertical and horizontal asymptotes and use that information to graph. So let's start here. If we had forgotten what this function looks like, I would be really sad, but we could always make a table of values to sort of figure out what the behavior is going to look like. So thinking about making a table, I know that I can't input an x value of 0 because, again, 0 in the bottom of my fraction is going to be undefined. So right away I'm going to have a vertical asymptote on the y-axis, which is where x is equal to 0, because in this case x cannot equal 0. So there's a vertical asymptote there. And then let's say I go to plug in positive 1 at 1, 1, I would have a point. If I plugged in 2, I would get a half. If I plugged in 3, I get a third. And as x is approaching infinity, so as this bottom of my fraction gets infinitely bigger, the value of the fraction is going to get smaller. So imagine we had 1 over 4, and then we eventually have 1 over 100, and then 1 over 1,000. So the bigger this gets, the smaller my fraction is going to get. So as we approach infinity, as x approaches infinity, f of x, our function, is going to approach 0. The fraction is going to get smaller and smaller and smaller, but it can't get to 0 because the top of the fraction has a 1 in it, so there will always be some value to my fraction. And the same is going to happen on the other side, except we're looking at negatives. When I put in a negative 1, I get negative 1. Put in a negative 2, I get negative 1/2. And again, my fraction is going to get smaller and smaller and infinitely close to the x-axis. So we're going to have a horizontal asymptote in this graph as well, because again, those ends are going to be approaching 0. So as x gets bigger infinitely and smaller infinitely, we know what's happening. But in between the values of 1 that I picked and 0 that I can't plug in, I have all these fractions. So I put a fraction in there. If I have 1 over a half, for instance, how many halves are in 1 would be 2. So at a half, I'm going to go up to 2. If I put a third in, there's going to be 3 thirds in 1, so it's going to go up to 3. And if I put a fourth in, I get 4, and a fifth in, I get 5. And the smaller my fraction gets, the larger my output gets. So we would say as x approaches 0, our outputs are going to get infinitely large. But we're only going to approach 0. We can't actually get there because that input is not defined. And the same thing will happen on the other side. These are just going to be negatives. So this is what our parent rational function looks like. We have the asymptote at x equals 0. The vertical asymptote at x equals 0. We also have this horizontal asymptote at y equals 0, so that y value of 0 not possible for that function. And then in quadrants 1 and 3, we see the branches of the graph. Okay? Now we know transformation rules are going to apply, so I'm going to skip down here for a second. If I wanted to apply my transformation rules, when I see my parent function and just transformations of that parent function, I should be able to use those to sketch my graph. So I know this, I know this picture, right? And then I know also that multiplying my function values by negative is going to reflect them over the x-axis. And I also know that adding 2 to my function values is going to make everything shift up 2. The question is, what am I shifting up to? What can I use as a reference point? So like a parabola, for example, if I was going to take my parent parabola and shift it up 2, I would just take the vertex up 2 and move all of the points with it. So that origin is a nice point of reference. Now for our parent rational function, we can still use the origin as our reference point, but we're going to let that be the point where our vertical and horizontal asymptotes cross, and then everything else will just move with it. So in this case, if my graph is going to shift up 2, then instead of my asymptotes crossing at the origin, they're going to cross right here at 2. So my horizontal is going to move up to positive 2, but my vertical is not going to move because it's not going left or right, so that's still there. So those will cross at 0, 2 instead of 0, 0. And then normally my branches would just follow, so I would just sketch a branch in quadrants 1 and quadrant 3. However, this graph is reflected over the x-axis, so this branch is going to have to go here, and this one's going to have to go here to make that mirror image. So now I'm going to sketch a branch into quadrant 2, and I'm going to sketch a branch into quadrant 4. And that's just a sketch, just so we have the basic idea of what's going on. If I really wanted to calculate this intercept, that's something I should be able to do, but not necessary if we're just sketching. Okay? So same thing here. I can see my parent function, and I know that just subtracting 1 from my input is going to make this graph shift to the right 1. So again, using the origin as my reference point, if I just go to the right one, this will be the point now where my asymptotes are going to cross. So the vertical moves this time, but the horizontal does not, because we don't go up or down. And we're not reflecting or doing anything else, so I'm just going to follow my branches. Make those branches approach those asymptotes in the new, like, quadrant 1, quadrant 3 locations. Okay, similarly here. Here's my parent function. And then I can see this negative. When I multiply the input by a negative, it's going to make everything reflect over the y-axis. And when I subtract 4 from my outputs, that makes everything shift down 4. So let me start with the shift down 4, starting at the origin, then go to 1, 2, 3, 4 units down. That will be the new point where my asymptotes are going to cross. So the vertical is not going to move. We're not going left or right, but the horizontal is now down at negative 4. And again, normally my branches would be here and here, but if I reflect over the y-axis, I got to go here and here with them. So technically, a reflection over the x or y has the same impact on these branches. They end up in the opposite quadrant. So instead of 1 and 3, we end up at 2 and 4. So that would be a reasonable sketch of this graph. And then another, here's 1 over x plus 3 plus 1. Again, there is my parent function. I know that this adding 3 to my input here is going to make everything go to the left 3, and adding 1 to my function values is going to make everything go up 1. So from my origin, if I go left 1, 2, 3, and up 1, this would be the new point where my asymptotes will cross. So let me sketch those in. And nothing is reflecting here, so I'm just going to sketch my branches in to the first and third quadrants, and boom, we basically have the concept of the graph. Okay, and this is ultimately something we want to be able to visualize, but it's hard to sometimes hold so much in our heads. So if we can at least make a sketch, this will be crucial to the work that we do in calculus. Okay, understanding the behavior of the graphs, what the ends are doing, so the horizontal asymptote affecting those end behaviors, and also what's happening as we approach the vertical asymptotes. Okay, so knowing those behaviors and being able to mentally visualize these graphs or make a quick sketch so that we can actually visualize is going to be super helpful. Now that's the parent form of our, these are transformations of the parent rational function. But there are a few other reciprocal functions that are worth looking at, so I want to show you a couple of those. So we looked at 1 over x. I want to look at next 1 over x squared, and then 1 over x cubed, and then 1 over x to the fourth. So some other reciprocal functions, reciprocals of some other polynomial functions to be specific, just so you can compare and see some similarities in some behaviors. Okay, so 1 over x squared. Again, if I input a 0 into this function for x, that's not going to be defined. Division by 0 is still no good. So this graph would still have a vertical asymptote here because x still can't be 0. Horizontally, what's going to be happening? So again, if I input a 1, 1 over 1 squared would still be 1 over 1. So that point's going to be the same. But when I input a 2, instead of having 1 over 2 like I did in the first function, I have 1 over 4. So I'm going to get smaller as my input increases. And again, input of 3, now it's 1/8, and then it becomes 1/16 and 1/32, but really the same behavior. This graph is going to be, as x approaches infinity, the bottom of my fraction gets bigger and bigger and bigger. The top of the fraction staying 1 means ultimately my fraction gets smaller. So again, a half to a fourth to an eighth to a 16th to this gets bigger, the fraction gets smaller. So we're going to still be approaching the the x-axis as we go this direction. And if I put a fraction in there, so if I have 1 over, let's pick a half. Well, now it's a half squared. Oh, pen. Technology loves me sometimes. 1 over 1/2 squared means we're really looking at 1 over 1/4, and that would be 4. So at a half, I'm going to go up to 4. And the same kind of behavior is going to happen that we saw over here, but faster. Like it's going to approach the axis faster. Okay, so this part of the graph really looks the same as the other part. I see this horizontal asymptote happening here. We're going to be approaching the x-axis, but we're not going to be able to get there. It's the next part where it varies a little bit. So we said in this function, when I say this one, I mean this one, that the same behavior in quadrant 3, or the behavior in quadrant 3 is the same as the behavior in quadrant 1. We're just inputting negatives and outputting negatives. That's an odd function. We see symmetry about the origin there. But and it should make sense. X to the first is an odd function. However, x squared is even. Whether I input a positive or a negative, my output will still be positive. So when I go to input a negative 1, 1 over a negative 1 squared is still going to be 1 over 1. So I get the same behavior here in quadrant 2 that I had happen in quadrant 1. So when I plug in a 2, I get an eighth, and plug in a 4. What did I say? A fourth, and plug in a 3, I get an eighth, and the values will approach the axis this way and get larger as we go this way. So my branches end up in quadrants 1 and 2 instead of 1 and 3. And again, this first one is an odd function. Not that it has an odd degree. That's different from the function being odd. When we say the function is odd, that means it's symmetric about the origin. So that's every point and its opposite. Or changing the sign of the input changes the sign of the output. Whereas 1 over x squared is even. It has symmetry with the y-axis. If we change the sign of our output, the result is the same. So positive and negative output lead to the same place. Okay? So that's what's happening with 1 over x versus 1 over x squared. Now I bet you can guess what's going to happen with 1 over x cubed. So again, I can't input an x value of 0. I can put 1 in. 1 would be a point. Put a 2 in, and 1 over 2 cubed would be an eighth. And then put a 3 in, and I get 1/27th. Put a 4 in, and I get 1 over 64. And again, the fractions will get infinitely small. And if I put in a half, 1/2 to the third power would be 1/8. There would be 8 1/8ths in 1. So at a half, we're going to go all the way up to 8. And again, this is just going to increase faster, but basically have the same behavior as 1 over x. Okay, just like 1 over x squared did. All have the same behavior in quadrant 1. But now when I cube a negative, I still get a negative. So when I input -1, I get a -1. And so we're back to having these branches in quadrants 1 and quadrant 3. So put in a -2 and I get -1/8, and these fractions will get smaller, and these will approach the axis this way. So as x goes to infinity or negative infinity, our outputs go to 0, and as x approaches 0, the vertical asymptote, from this direction, we would say as x approaches 0 from the right side, that the y values go up toward infinity, and then from the left side, as we approach 0, the y values go down toward negative infinity. Again, behavior you will talk about when you go to calculus. And then if I look at x to the fourth, it should make sense that 1 over x to the fourth is going to basically do the same thing that 1 over x squared did. Now, all of these have the same behavior in quadrant 1. They all have this vertical asymptote here, can't input a 0 for x. And, excuse me, 1 over x to the fourth. So if I plug in a 1, 1 to the fourth is still 1. But then when I plug in a 2, I get 1/16. And so this thing is going to drop down and approach the x-axis faster than the other did, than all of the others did, but basic same behavior. And if I put in a half, 1/2 to the fourth would be 1/16. There would be 16 of those in 1. So at a half, I'm jumping all the way up to 16. So it's going to grow much faster as we go this way. And if I raise a negative number to the fourth power, I'm still going to get a positive result. So my branches are going to be in quadrants, again, 1 and 2 instead of 1 and 3. Alright, so we can make some generalizations here, and hopefully these pictures make sense, and you will see some of these things come up. So characteristics of reciprocal functions that are worth noting. And these are, again, in parent form. There's no transformations here. We have a vertical asymptote happening for all of these at the restricted x value, which was 0. The function values at both ends of all of these, all of them, the end behaviors, they all approach the horizontal asymptote at 0. So they approach 0. That means the function values, right, are approaching 0. So we have that horizontal asymptote happening at y equals 0. The only distinction between the four reciprocal functions we looked at was when the degree of the denominator was even versus when it was odd. So when it was an odd degree, we saw an odd graph. That's what symmetry about the origin, right? Where you input a positive, get a positive, input a negative, get a negative. And when it was an even degree, like the square of the fourth, input a positive or a negative, and the result is still positive. So that's symmetry about the y-axis. If the degree was odd, like the first three, then those graphs were symmetric about the origin, which are odd functions. And then if the degree of the denominator was even, then we saw that symmetry about the y-axis, and we call those even functions. So I'm saying even and odd twice, but I'm referring to different things. So an odd degree does not always mean that the function or the graph of the function is actually odd. It has to have that symmetry in order for the function to be considered odd. Let me just show you real fast so you can understand. Like if I'm looking at x to the third power, that is an odd graph there. The graph has symmetry about the origin as every point in its opposite. But if I was to, let's say, shift this to the right 5 times, okay, then it's still an odd degree, but it no longer has the symmetry about the origin. So an odd degree does not necessarily mean that the function is symmetric about the origin, okay? And same for even degree versus even functions. So again, if you had an x squared, right, that's an even degree, and it's also an even function in that it has symmetry with the y-axis. But if I shift this over to, let's say, the left this time, 2 units, it still has an even degree, but it no longer has a symmetry with the y-axis, so it's no longer an even function. Alright, so I don't know why we use the same terminology in different ways, but remember, I'm the messenger here. Okay? So we have a whole bunch of our, let's see, reciprocal functions. We've got the parent one down, we've got the transformations down. Now, we need to sort of generalize, because not every rational function we're going to see is going to be in some parent form. How do we go about finding our asymptotes so that we can make the graph of any rational function? So generalizing, vertical asymptotes I think are the easier. They're just a little bit more intuitive. Vertical asymptotes happen, so think about all those the parent one that we did and all the reciprocal ones we did, where we had the vertical at x equals 0 because that value of x made a 0 in the bottom of the fraction. So anytime we're looking for a vertical asymptote, we're looking at any restricted x value. That would be any x value that makes our denominator equal 0. If the denominator is equal to 0, that is undefined, that's going to cause a vertical asymptote. So we would set our denominator equal to 0 and solve if that was necessary. I'm hoping we can just see these vertical asymptotes, but if we need to do the work, that's the work. Set it equal to 0 and solve. Like number 1, for example, if I said find the vertical asymptote, I can see an x value of 6 input right here is going to 0 out that denominator. So I would have a vertical asymptote at x equals 6, or I could say x could not equal 6, and that's why a vertical asymptote happens there. Here, I know there's going to be a vertical asymptote at x equals positive 3 over 2. That would be the x value I could input to make a 0 in that denominator. Here, I might want to look at this in factored form. x plus 2 and x minus 2, or again, if you're just solving, add the 4 over, take the square root. In either case, there would be two vertical asymptotes here. X would be positive and negative 2, or can't be positive or negative 2, so two vertical asymptotes would occur. And maybe it's helpful for you to see. Again, I'm just trying to find the x value that makes that denominator equal 0. That's where my function has a vertical asymptote. So on this last one, again, what would make 4x plus 1 equal 0 would be, in this case, a negative 1/4. So finding the vertical asymptote, pretty straightforward. It's finding the horizontal that's a little tricky. It takes a little bit of thought, maybe a little bit of memorization after we think through some of this stuff. But ultimately, they can be found by comparing the degrees of the numerator and denominator, because they're going to dictate the behavior of the graph at the ends, which is really what our horizontal asymptote is affecting. It's those end behaviors. So the first case I want to talk about is the same case we saw in our parent function. If the degree of the numerator is greater than the degree of, oh no, backwards. The degree of the numerator is less than, the degree of the denominator, then the horizontal asymptote is going to be at y equals 0. That's exactly what we saw happen with the parent function. So if the degree of the numerator is less than the degree of the denominator, so if we look at the parent function, y over x, technically the degree of our denominator is 1, and the degree of our numerator would be 0. Remember, the degree is what is the maximum number of variable factors we see in any one term. So it's bigger on the bottom. And if it's bigger on the bottom, it means the bottom of the fraction is going to grow faster than the top of the fraction. So if the bottom is growing faster, that means the value of the fraction is going to get smaller and smaller and smaller and infinitely small until it approaches 0. So that will be the same even if I had like an x to the second over an x to the third. Now I know that this form reduces, but ultimately there would be like more stuff here, right, that we might not be able to reduce. But if the degree of the bottom is bigger, it's going to grow faster. And if it's growing faster, if the bottom of the fraction is getting bigger faster than the top of the fraction is, then your fraction value has to approach 0. So hopefully that makes sense. That will be just like our parent function. If the bottom denominator is bigger, or the degree in the numerator is smaller, whichever way you want to think about that, it will behave just like the parent function in terms of horizontal asymptotes. That horizontal will be at 0. Now, if the degree of the numerator is equal to the degree of the denominator, then what we're going to do is a little bit of division. We're going to divide the leading coefficients to figure out where our horizontal asymptote is. And again, I'm going to hope this makes sense. Let me try to show you. So if, for instance, you had, let's say, 4x plus 1 over x minus 3, okay? What I'm saying is, to find the horizontal asymptote, you're going to divide the leading coefficients, which in this case would be 4 divided by 1. So this is going to have a horizontal asymptote at y equals 4. Now, why does that happen? Now, remember what the fraction bar means here is these two polynomials are technically being divided, right? If I actually divided here, and I can use synthetic division for this, I would have a positive 3 outside of the box here. That's the 0 for the divisor. Inside the box, the 4 and the 1. So the 4 here and the 1 here. What happens is we bring this down, multiply, we get 12, add, we get 13. So what are we looking at here is a constant and then a remainder. So that means this 4x plus 1 over x minus 3 could be rewritten. This quotient is exactly 4 plus a remainder of 13 over my divisor, which was x minus 3. Well, this form of my function is a transformation of my parent. What I see here is a vertical stretch of my graph by a factor of 13. I know it's going to shift over to the right 3, and this makes everything shift up 4, including that horizontal asymptote, right? Goes up to 4. And if it was a different function, let's say it was 6x minus 5 over x plus 2. Again, if I go to do the division, the 6x, oops, 6 and the minus 5 here, this is going to come down. And so if I just divide the 6 by the 1, I'm going to get that 6 there. That's the 4 that's there. That's where my horizontal asymptote is. Now you might be wondering, and maybe it's a little weird for you to look at it, like what if I had a, I don't know, 8x plus 2 and I was dividing by a 2x minus 3? Maybe we look at the long division, 2x minus 3 dividing into 8x plus 2. When you start the division, you're going to divide the first term by the first term. That's going to get you 4. Again, that's where my horizontal asymptote is going to be. That's going to be the constant that we see here. So I can just shortcut by dividing these two numbers to find that horizontal. That's when our degrees are equal, right? If I divide a line by a line, the first result of my division is going to be that constant, okay? And then the other case is what happens if the degree of the numerator is greater. If the degree of the numerator is bigger, so if I have like an x to the third divided by an x squared, then the top of the fraction is going to grow faster than the bottom. So imagine in the parent form if you had x over 1, well, this is going to get bigger, and then dividing by something smaller has very little impact. So you're just going to have something that grows without bound. There isn't going to be a restriction. You're just going to see things get bigger and bigger and bigger, so n's will be going up toward infinity, possibly down toward negative infinity, but not the same restriction where we have a fraction that gets smaller and approaches 0 or zeros out. So if the degree of the numerator is bigger, if the top is bigger than the bottom in terms of degree, then there is no horizontal asymptote. Something else could possibly happen, but we'll talk about that something else later. Okay, so we found all the verticals, let's find the horizontals. So here, horizontal asymptote at, these are the same degree, so I can divide here and say would be at y equals 3 divided by 1, which is 3. Horizontal asymptote here, the degree of the top is 2, the degree of the bottom is 1. That means 2 being bigger than 1, the top's going to grow faster. There's not going to be a horizontal asymptote here. No horizontal asymptote. That looks strange, abbreviated. Here, degree of the top is 1, degree of the bottom is 2. Just like the parent function, the bottom's going to grow faster than the top. That means our fraction is going to get smaller and approach 0. So horizontal asymptote at y equals 0. And then lastly, we have degree of 1, same degree. So I would divide my leading coefficients and say that this horizontal asymptote would be at y equals 1/4. Okay? So if we're looking at graphing a transformation of the parent function, easy to make the sketch. If we're looking at graphing a rational function, I'm so sorry. I need to get some water or something. I just don't have any handy. Alright, if we're looking at graphing a rational function that is not in a, well, it's not just a transformation of our parent function, right? I don't just see a 1 over x in number 4 here, for example. But if I can figure out where the asymptotes are, which I know I can do, and then I can use a table of values to find some other points, maybe find some intercepts, and still make a good sketch of my graph. So looking at this picture, or looking at this function, I know my vertical asymptote is going to be at an x value of -1. That's the restriction there. So let me go ahead and plot this in my graph. I'm going to go to x equals -1 and say, alright, I'm going to have a vertical asymptote through that x value. It's no good. Okay, horizontal asymptote. Let me change colors. If I want to find the horizontal asymptote, I'm going to compare the degrees. And these degrees are the same. They're both linear. So I could divide these leading coefficients and say the horizontal asymptote will be at 4 divided by 1, which is 4. So I'm going to go to y equals 4. Say, okay, my horizontal asymptote has to go through that y value of 4. Now the only other thing I have to do is figure out the branches. I have to have a branch on either side of my vertical asymptote. I just don't know if is it going to be branches in quadrant 1 and 2, is it quadrants 1 and 3, is it 2 and 4, where are the branches going to be? And so to figure this out, I just do a quick table of values. So when I make my table of values, what I want to do is pick x's left and right of my vertical asymptote. So I have that vertical asymptote at -1. Maybe I input an x value of 0. That would be a nice one to plug in. So 4 times 0 minus 5, and then 1 times 0 would just be 0 plus 1. I end up with -5 over 1, which is -5. So if I have a point down here at 0, -5, that means that my branch has to be in this quadrant that's created here. Now, if I wanted, I think another reasonable thing to do would be to find the x-intercept there, which is I could do by inputting a y, but if I'm just ultimately trying to sketch this graph, I think this is going to be good enough. If my point is down here in this quadrant, right, that is where my branch has to be. So I know I'm going to be approaching the asymptote this way, and then I'm going to have to be approaching the asymptote this way. So this would be a reasonable enough sketch of that branch. The other question is, where's the other branch? Is it going to be next to it in quadrant 3, or is it going to be up here in quadrant 2? Right? This wouldn't be an option because then we wouldn't be looking at a function. So the options are quadrant 2 and quadrant 3. So let me pick another x value that is on the other side of that vertical asymptote, like -2. If I plug -2 in, that would be 4 times -2 minus 5 over -2 plus 1. So that's -8, -5, -13 in the numerator, -1 in the denominator, so positive 13. So at -2, if my graph is way up here at 13, again, that's an indication that this branch has to be in this quadrant. And there I did it. Sketched my graph. Okay? And if I wanted to, again, calculate the intercept for the branch that I put over there in that fourth quadrant of the shift, then I could, but I'm just really trying to get a good sketch, an accurate sketch, but not, all the details. This would be totally fine. Alright, so let's try another one here. Number 5, the final one. If I want to find the vertical asymptotes, I have to figure out what makes this denominator equal 0. This would be easier to do in factored form. Factors in -20 that make -1 would be -5 and 4. So this thing is going to factor into an x minus 5 and an x plus 4, which means there would be 2 vertical asymptotes. Vertical asymptotes at x equals 5 and at x equals -4. Those would be the 2 values of x that make the denominator equal to 0. No good. So I'm going to go to x equals 5 and say, okay, I'm going to have a vertical asymptote there. Go to x equals -4 and say, alright, got to have a vertical asymptote there. And I don't know what happened. It started to all blur together. Okay, so there's those. And now let's find the horizontal. If I compare my degrees, the degree of the bottom is 2, the top is 1. That means the bottom's going to grow faster. If the bottom grows faster than the top, then the fraction value is going to approach 0. So horizontal asymptote, just like the parent at y equals 0. So horizontal at the x-axis, right there. Okay, so now I got to figure out where my branches are, and there will be 3 this time. So I'm going to have a branch. It's either in quadrant 1 or quadrant. Well, I don't know. They're not really quadrants anymore. This is 6 places, but I'm going to have some branch on this side of the vertical asymptote, some branch in between, and then some branch that's over here. So I got to figure out what those are going to look like. So I need to pick x values left of, in between, and right of those verticals. So let's do it. And did I call this function y? Yes. And okay, so I'm going to start on the left this time. So my leftmost asymptote is going to be at -4. So maybe I plug -5 in and see what happens. If I plug a -5 in, and I'm going to use a calculator for this. I don't want to screw it up, and I'm going to have to do a multiple here. So -5 plus 2, and then I got -5 squared minus my -5, and then minus 20. Okay, so I get -0.3-ish. -0.3-ish. So if at -5, I'm at -0.3, right, I'm going to be down here. That means my branch has to be down here, approaching this asymptote and approaching this asymptote. Has to be. Okay, I can't have a branch go up here, because then again it wouldn't be a function. So there's the one branch. Now what's happening in the middle? Lots of different things actually can happen in the middle. Sometimes you get this like parabola happening. Sometimes you get something that looks sort of cubic in here. Um, so we're going to need to pick a few points to see what's happening in between the two asymptotes. So maybe I pick like, let's see, -2, 0, and +2. -2, 0, +2, just so I get a good idea, and if I need more, I can pick more. So now I'm going to replace these -5s. Let me put -2 in. Oh, I can already see what's going to happen there. It's going to be a 0 because the numerator ended up being 0, so we got an x-intercept, which is kind of nice. Let me replace the -2's with 0s. And I can already see what's going to happen on this one too, but just so you can see it as well, we're going to end up with -0.1, and then I'm going to plug a +2 in, and we're going to end up with -0.2-ish. And I don't need to carry too much of that decimal because I can't see the difference in my graph anyway. Okay, so at -2, our graph is at 0. At 0, our graph goes down to -0.1-ish, and then at +2, my graph is negative again, and it's further negative, so -0.2-ish. It appears that this is going to keep decreasing, but maybe I pick another. Let me go ahead and swap this out with a, let's get closer. Let's put a 4 in there and see what happens. Just want to make sure. And yep, -0.75. So at 4, we're going to be down. I messed this point up. This would be like -0.1, -0.2, 0.7. Yeah, these are going to keep decreasing. So it looks like this is going to, wow, that looks terrible. Going to be decreasing and approaching this way. Now, after -2, is it possible that the graph turns back this way? Sure. So let me go ahead and plug in a -3 just to be safe. Do I increase or do I decrease? Do I head down or do I head up? I need to know. So I'm going to put this in as well. And -3. And now we're positive, okay? So because we're positive at -3, then the graph is going to have to go up toward this asymptote, okay? So again, you can see parabolic or sort of cubic behavior. All kinds of weird things can happen in between two asymptotes. So more values you can pick, the better. And then lastly, the other side will be easy. What's happening on the other side of the vertical asymptote? Let's go ahead and pick +6. And I already have this here, so I might as well just use it, right? +6, +6, and +6. We end up with 0.8. We get a positive. So if at +6 we're at 0.8, we're positive, we have to be in this region. So we want to approach the asymptote this way, and again, approach the asymptote this way, okay? Now, you're not going to get a graphing calculator when you take your quiz, but while you're practicing, it would be helpful to know if you did this right. So let's go ahead and just confirm our work. I'm going to put a fraction in here. On the top, x plus 2. On the bottom, x squared minus x minus 20. And it looks like my picture, but I want to just be extra sure. I said at x equals 5, vertical asymptote, that looks right. I said at x equals -4, vertical asymptote, that looks right. And then I said at y equals 0, a horizontal asymptote, which is affecting my end behaviors. And yeah, all that looks right. I can see my branches approaching. I can see that weird sort of cubic looking thing in between the asymptotes. And so I think I'm in good shape. Alright, so make sure you're using technology to verify your work while you're practicing, but note, you're not going to get that. You'll have your scientific calculator for your quiz, but not the graphing. So, like making the table of values, that would still be something you could do with your calculator. Okay? I think you should have enough to get going on your assignment, but as always, if you need some extra help, then reach out. Till next time, take care.